Say it again. Yeah, so we're going to factor that. That's difference of squares, right? So then we have x minus 5 over x plus 5, x minus 5. And so then these can cancel. And so then really what we're doing is 1 over x plus 5. So now what? Yeah, right. So now we can plug it in, and it's just going to be 1 over 10. And so then that's the limit as x approaches 5. So then they go down to, I don't know which one they do first, but right from the left. And we're still going to use x plus 5. So yeah, so here's what the question is. So if it was 1 over like a positive, like very, very small positive.
1 is constant then. Like the 1's not ever going to be.
It's going to be always 1. And so the whole idea of this, and it's going to be the same idea today, well, not the whole idea, but like if you're dividing any constant by a super, super, super big number, it's going to 0. And so like 17, is that what you said? So yeah, I mean, it's always going to be 1 over whatever. So it could be going, and this is what we're checking, right? Like it's either going to go to infinity when you get super close to it, and that's where you have to check a little bit bigger or a little bit smaller, because we're seeing if it's go to positive infinity or does it go to negative infinity, do they agree, and all that kind of thing. Or it doesn't go to infinity at all. So if it goes to infinity when we're doing this, then we say vertical asymptote. If it doesn't go to infinity, then we say it's not a vertical asymptote, because that's what this is actually asking to find the vertical asymptote if they exist, right? So is this to negative 5? Oh, this one's to negative 5. Sorry. Yeah. Okay, so then if we're going to negative 5, then we would still get like 0 in the denominator, right? So it's going to go to either positive or negative infinity. So then if we're coming from negative 5 from the left, is the denominator going to, what's the denominator going to? Like a positive value or a negative value? It's going to a negative value, so this is going to negative. Like you were saying, this is staying positive. So then we're going to say this goes to negative infinity. And so just like to kind of finish the thought on this, this one, even though it can't be 5 because like of this is not producing a vertical asymptote because it's actually going to 1/10. Okay, this one is going to be some kind of vertical asymptote because we've already gone to negative infinity. So is that okay? All right, so then we also want to come from the right, because we're trying to think, well, is it going to the same place or not? So same kind of question. If we're coming from a little bit from the positive, so like negative 4 point whatever, is that producing a positive or negative down here? So that's going to be a positive. Again, this is going to remain positive, so then this is actually going to infinity. So it's still a vertical asymptote. They just don't agree. One's going up and one's going down. So then the vertical asymptote's at negative 5. And so again, like I'm not asking you to ignore the stuff we talked about like in pre-calc. So if you have values that when you plug in to the denominator you get a 0, they will either be a vertical asymptote or they will not. But they're not allowed to be plugged in there no matter what. So if you cancel them, and that's what happened like on this first one, right? We ended up canceling the one that gave us a 0 down there. So this one's not a vertical asymptote. This is just how it all works. This is why this is actually like the real math to it instead of just remembering like the steps. So, okay. All right, so anything else from that section? So then, right? So then, but these are the review from that then. So you guys don't have to graph it, just show it with your hands, right? So use a graph to explain the meaning as x approaches a from the right of negative infinity. What's that looking like? Right, yeah, it's coming this way and going down, right? Coming down. It's going to negative infinity. So then if it's coming just to a to positive infinity, what is that implying? Is it, but this one, so the only thing I would point out is this is just to a, not from the left or right, so it'd be like kind of coming at it and going up like this, okay? All right, so what is a vertical asymptote? Okay, so you're going to have to be careful on that. That is the definition you use as asymptotes before you know what an asymptote is. So that's for the people that aren't going to be in this class. We tell them that. But for you guys, like, give me a better definition of a vertical asymptote. Okay, so like, give me the whole thing. As we're getting closer and closer to. So some value A, as we get closer and closer to some value A, the limit approaches. So if it's a vertical asymptote, yeah, positive or negative infinity, right? So, you know, even better, like maybe even a better definition is as we get closer and closer to this value A, the limit keeps growing arbitrarily larger and larger and larger. Okay, so then it's going to infinity or negative infinity. Is that right? Okay. I'm not going to read all that, but we got f over g with g of a equaling 0. Does f necessarily have a vertical asymptote then at a? So give me, so on a statement like this, you got to give me all the things that could happen. Like, is it, so the question is it always going to be a vertical asymptote there if the denominator is 0? No. What else could it be? If it's not a vertical asymptote. Just like a hole. Yeah, like a hole, right? Like, so then how does that work? How would it give us, if we plugged in a and we get a 0 in the denominator, and it's not a vertical asymptote, what has to have happened? Something, yeah, the numerator factors and you cancel it instead of it. So again, if it's canceled, it's still undefined, so there's a hole. If it doesn't cancel, that's where we get our vertical asymptote. Suppose we're going to 100 and 0 with all that from the, okay, so as x approaches 2. Say it again. And so then what's going to happen then? Why are you saying negative infinity? Is that okay? Going to negative infinity? All right. Then number 6. This is the whole thing. Number 6 is the whole thing. So the limit as 3 approaches from the left, what is that going to be, positive or negative infinity? Why is it negative again? So like 3.5, negative 3.5, or I'm sorry, 2.5, sorry. And so then that would be a positive over a negative, so negative infinity. And then if we're coming from the right, because it'd be like 3.5, so we get a positive over a positive. Is that right? All right. One more of these. Right, it's 41. Vertical asymptote at 1. Question. Top factors in the x minus 1, x minus 6. Okay, so what denominator is left then? Oh, what's happening?
X
No, don't do
plus
that.
1 on the bottom.
Oh, I get distracted. Say it again.
I think it would be false because you'd be left with X plus 1 on the bottom.
So you're left with x plus 1 at the bottom.
And so the vertical asymptote couldn't be 1 because that doesn't get you here.
And that one got canceled.
Yeah.
Okay, so then part A is false, but then part B is true, right? Because that negative 1 is still there. Right? Because you get x plus 1 set it equal to 0, subtract 1. Is that okay? And if G has a vertical asymptote at 1, and coming from the right you go to infinity, and coming from the left you go to infinity. Oh, that has to happen. Is that true? So basically they're asking, if there's a vertical asymptote, do they both have to go in the same direction? Right? One could go, it's still a vertical asymptote, but one goes up and one goes down. All right, cool. We are doing the next section, and the next section is starting on page 96 and 97. So here's the basic rundown of this. And again, we've talked about these before. This is stuff from pre-calc, and in fact, they give you the same statement, which is nice because then we can use that. But limits at infinity means that the x value is going to either positive infinity or negative infinity. Okay? So it could be that when we go to positive infinity, our limit goes to positive infinity. And it could be as x goes to negative infinity, it goes to positive infinity or negative infinity. But all of these are definitely x is going to approach positive or negative infinity. Now this is also called end behavior. So you guys have actually done this a little bit before. And this is just going to be the math of how it works. Now, you guys are going to have to tell me how you want to go through this. But they give us this first example here. And this is just to tell you, okay, here's what horizontal asymptotes are, right? So they give you this function, tangent of the inverse tangent. If you don't remember what it looks like, there it is. And what they're saying is we go, right, the domain on this is negative infinity to positive infinity. So if we go, as x approaches positive infinity, right, the y value or this function ends up getting closer and closer to pi over 2. And if we go to negative infinity, it gets closer and closer to negative pi over 2. And so then when that happens, you call it a horizontal asymptote. Fair enough? Okay. And so then they have this definition right down here, right, of exactly what that is saying, right? If you can make this statement, if it goes to a value L, just like anything else, right? So L is going to be a number. So as you go further and further down the x-axis, if it approaches a value, then you say that's a horizontal asymptote. Okay? So not all end behavior has a horizontal asymptote. In fact, I guess most probably don't, I guess. All right, so then positive and negative infinity, both are true. So if you go down to the right as far as you go and it approaches a value, then that's a horizontal asymptote. If you go to the left as far as you can go, maybe it goes to the same value, maybe it goes to different values. But if it goes to a value, you call it a horizontal asymptote. If it does not go to a value, then we're going to say something else. It's going to be the infinity stuff again. So then this quick check is worth looking at. You don't have to, like they say, as limit, you can do the 10, the 100, or the 1,000. But as we go to infinity of x over x plus 1, what is that value approaching and why? So, like on this quick check one, they're saying, like, here's this function x over x plus 1. And they're telling you to evaluate it for 10, 100, 1,000. You can do that if you want, right? That would just be 10 over 11, 100 over 101, 1,000 over 1,001. And so then as we keep plugging in bigger and bigger numbers, what is this limit going to approach? So she's saying 0, 0. And so you guys are all saying 0, so then why are you saying that becomes 0? Say it again. So, alright, so here's a way to think about it. If you had $1 and then you had a penny in your pocket, and someone was like, how much money have you got on you? You might say $1.01. Okay? Then if you had $10 in your pocket and also a penny, there's a chance that you would say, I got $10.01. And maybe if you got $100 in your pocket plus a penny, you might say, oh, I got $100.01. But I would argue that eventually you would say, if you had $10,000 in your pocket and a penny, you probably aren't going to mention that penny anymore, right? So the bigger and bigger we get, the more irrelevant that penny is. Does that make sense? So then, if we're talking about 100 trillion over 100 trillion and one, is there any real significant difference between the two? Okay, so then it's not going to go to 0. What's it going to go to? Well, it's really just going to 1. It's basically 1, right? Okay. So that's the ideas we're going to play around with. And if you notice, this goes back to our pre-calc stuff. If you notice, what is the degree of the numerator there?
1.
1. What's the degree of the denominator? 1. Okay? So we'll keep that in mind. All right, so again, you guys got to tell me what is going on, like what you guys want to do with these examples. And we can do some of your homework. Off to the side of this example, they talk about how, hey, by the way, all of our limit laws still apply, and also the squeeze theorem still applies, even though we're going to infinity. Okay? So then they give you this example, and I'm going to point out that part A here is kind of the whole idea of what we're talking about. We're going to have this denominator that is just going to grow without bound over something maybe that will not. And that's going to be nice for us because that's going to always go to 0. All right, so then if that part A, if you're plugging in bigger and bigger values as we approach negative infinity, it really becomes irrelevant. And so then this value that limit is approaching ends up being 2. Because it's really like 2 plus 0. Okay, so then you're going to say there's a horizontal asymptote at 2. And so then on part B, and I'll just talk through it, and then maybe we can do some examples here. We got to get a little bit further before we do some. Right, it's the same kind of idea. So we're saying, okay, so they're using they're going to use the squeeze theorem with this. And normally the squeeze theorem is more like you need to recognize it when they show it to you. But like on here, they're saying, well, if you remember what sine does, right, it just bounces up and down. And normal sine just ends up going between -1 and 1, right? So it's never anything besides -1 and 1. And so then what they're saying down here is since that's true, then it's going to fit between these two things. Because like sine would be like the one on the left is -1, and the one on the right is +1. So they're applying the squeeze theorem here. Again, I wouldn't overly worry about like, do I have to come up with those functions, as long as you can say, okay, that makes sense that those two would be bookending that middle one. So is that okay? And so then what they say below that is, okay, so then if you're okay with that, then because we have a variable in our denominator, as that grows and grows and grows and grows, both of those are going to 0. So that must mean that sine of x over radical x is also going to 0. So it actually doesn't matter that it's being multiplied by 3 and it's going to 0. Fair enough? All right, they kind of talk about that more there. All right, so then here's some stuff that you should kind of already know. So it could happen that as we approach infinity, our limit goes to infinity. Or as we approach infinity, our limit goes to negative infinity, and vice versa. Okay, so what we're talking about now is x is always going to infinity, other things may happen. And this is more of an end behavior kind of situation. And if you guys remember last year, I was like, oh man, it'll be so much easier if you guys remember the shapes. Okay, so then this one is probably x cubed. Yeah, so that figure there is x cubed. But is it okay to say that any odd function, or rather, if the biggest degree is odd, it's always going to be relatively close to that shape? Okay, and so then any polynomial, and then we're going to look at this more closely, any polynomial whose lead term has an odd exponent, ignoring whether it's positive or negative, as we go to positive infinity, the value is going to go to positive infinity. And as we go to negative infinity, the value is going to go to negative infinity. Is that okay? What's that? That's if your biggest exponent is odd. It's always going to be basically that shape. Okay, so then, here's both the situations. Why is that happening? Go away. Go away. Okay, so the thing on the left, all even, right? If the biggest exponent is even, all of them look roughly like that. And so as we go to positive infinity, the function approaches positive infinity. As we go to negative infinity, the function approaches positive infinity again. Okay? So those are ones that you got to keep in mind. And so then, and they go through a little bit of that. So then we come to this statement, and this statement is kind of obnoxious, but if you look at it, basically what they're saying is let's not, let n be a positive integer. So let's not mess with negative exponents. That's what that's saying. So ignoring negative exponents. And all of our polynomials are going to be in descending order. Okay, so we're not tricking you, right? There's not going to sneak one in at the end. Okay? The biggest exponent is always going to be in the first term. If that's true, and n is even, then just like what we said, in both directions on the x-axis, the y values are going to positive infinity. Okay? And then if it's odd, as we go to positive infinity, the value is going to positive infinity. As we go to negative infinity, the value is going to negative infinity. All right? Okay, and then they say, all right, let's say that we have 1 over some value. Well, again, a constant over something growing unbounded is going to always go to 0. Okay, and then this last one basically is just saying, be careful if your coefficient is positive or negative. Okay, so for instance, I guess I'll do it here. Right? If we're looking at right, if we're looking at x cubed, right, it's going to go like this. This is x cubed. But if we look at negative x cubed, then it's going to go like this. So don't just look at the the biggest exponent, because that negative exponent or that negative coefficient is going to flip the thing around on it. So both of them matter. Is that okay? Okay. So let's look at some of your homework then. Because they say we should know up to 24 now. So let's look up until we get. So your homework is to get to 43. So we're like 9 to 43. I'm going to skip 9, 11, and 13, but here's what I will say. 9 is super straightforward. 11 and 13, you're going to use some version of the squeeze theorem. And if you notice, they give you a numerator of cosine basically in both of them. So it's always bouncing between -1 and 1. So you can just follow that example in the book. Is that all right? All right, so then let's look at 15. We can actually get some of these done. We can get several of these done, actually. So 15. Right, the limit. We get a bunch of these done. As x approaches, was that positive infinity? Of x to the 12. Why is it positive infinity? Because it's an even exponent and a positive coefficient. Is that right? All right, so then 17. Limit, is that positive infinity again? And then it's x over x to the negative 6. So what's the negative exponent do again? It goes to 0 because the negative exponent flips this thing upside down, right? So if you have a constant in the numerator and your denominator is growing without bound, it's going to 0. Should we do the rest of these, or 19 and 23, or what do you guys want to do? It's up to you. I'm going to say that means that you're happy with that. Let's move down. Oh, that was up to 24. Okay. Now we got to keep moving. All right, so get on page, we're on page 100 now. So again, we're about to get to theorem 2.7, which is on 101. And the way it works is that once you have a theorem, then you can just use that theorem. So all example 3 is showing how you get to that theorem. We're going to look at one of them to see how it goes, okay? So I'm going to pick actually we can do a couple of them. So this won't take long. So if we're looking at their examples, and they say f of x equals 3x plus 2 over x squared minus 1. Okay, so we need some information that actually does us some good. All right, so what we're going to do is basically multiply by some value of 1. So I'm going to take this and I'm going to multiply the top by 1 over x squared. I'm just taking the denominator, and the bottom over 1 over x squared. Okay? And the reason I'm doing that is I'm going to force it into, because what we're finding here is the limit as x approaches infinity. So I'm going to force it into something that produces a lot of zeros for us. Okay? So is it okay to say that now this is 3 over x, this is 2 over x squared, this is 1, and this is 1 over x squared? Does that make sense? Okay, and so the reason that this is nice is that we get a value down here in the denominator. Oops. Okay, as opposed to 0 or infinity, that doesn't do us any good. But this value will go to what if we're going to infinity? So a constant over something growing very, very large. 0, what's this one going to go to? 0, what's this one going to go to? 0, so then what we would say is, okay, so this is going to 0 over 1, so then it's going to 0. Is that right? All right, so then we're going to do the same thing for part B. All right, so then they give us this g of x equals 40 over x to the 4th plus 4x squared minus 1. Oh, and I want you to notice on that first one, the denominator had a bigger degree. Hopefully that reminds you of pre-calc a little bit. Okay, so same kind of situation. We don't really have any good information. This is the math part of it, okay? Then you're going to use the theorem here in a second. All right? So then we're going to multiply by 1 over x to the 4th. So then as the limit as x approaches infinity, then we have 40 plus 4 over x squared minus 1 over x squared. Oops. 10 plus 8 over x squared plus 1 over x squared. right? So then as we evaluate all those ones with x, they all go to 0 again, yeah? So then we're at 40 over 10. So then 4.
If it's just like 1, why isn't it 1 over x to the 4th and like?
It should be. Sorry. Yeah, you're right. Yep. This should be over 4th. Thank you. Is that okay? All right, and then the degrees were the same. All right, so to save some time, right, because we're going to run out of time here before we need to, right, the same kind of situation for part C. And then what you're going to see is that it goes to, just some, it doesn't exist. It just like goes to infinity. So then down here at the bottom of page 101, we have all these statements that we have. So right, if the degree is less than, if the numerator has a smaller degree than the denominator, right, then we're going to 0. And that means there's a horizontal asymptote at 0. If they're equal, then you take the leading coefficient of each, put them over each other, and that's what that value is going to. Right? So then that's where a horizontal asymptote happens. And then when the numerator is bigger, there is no horizontal asymptote at all. Is that okay? All right, so let's do more of your homework then. So 25, right? You're going to use that theorem. So they're the same, so that means the horizontal asymptote is 1/5, right? 4 over 20. So again, as x approaches infinity, the y value approaches 1/5. And so then we say there's a horizontal asymptote at 1/5. Is that okay? All right, what about 27 then? Say it again. They're the same again. So then as x approaches infinity, y approaches 2. So we have a horizontal asymptote at 2. And again, you can use that little trick of dividing through by the biggest variable, or the variable with the biggest x on it. But we have this theorem, okay? So then 29. Is the same? Oh, 0, right, because the denominator is bigger. So it's going to grow much, much faster. Is this okay? All right, so then we're almost there. So then 36. So in the book, again, you guys should be reading this, it talks about if it's a rational function or a polynomial, a rational function only has one horizontal asymptote, period. It could have a ton of vertical asymptotes, but it only has one horizontal, if it has one. Okay? But then they call these algebraic functions, like I'm looking at 35 to 38. And so then you can't say that there's only one. There could be more than one. And so then, like if we look at 36 as your example, we have to use this little trick, and we're going to go both directions. And so now I'm going to, again, multiply by some version of 1. And in this case, it's just going to be 1 over x. But inside the square root, right, the square root of x squared is x. So then really inside the square root, we're looking at this situation. Is that okay? So really, it's still 1, it's just inside a square root. Is that okay? All right, so now as we evaluate this, what's going to happen? Yeah, so that one goes to 0, so it ends up being the square root of 1 over 2 plus 0. So then it goes to 1/2. All right, but if we go to, well, on this one, if we go to negative infinity, I think we're still okay. Yeah, so like sometimes, like, so if you flip back to page 102, so actually we do have to evaluate it slightly different. And like the way, that, so like on 102, they say all this stuff and you can look at the example, but if you look over on the side, they talk about how the square root of x squared is the absolute value of x. So we're actually, like the way I think about this is like if you take a square root, you get a positive and a negative value. And so then like if we go out to negative infinity, everything's the same except that we're kind of evaluating this situation. That's supposed to be a 2. And so then we ended up getting the other asymptote is at negative 1/2. So again, the way I think about it is like, okay, I'm taking a square root, so I need a positive and a negative value there. What do we got? 6 minutes? All right, we're doing good. All right, so then power functions, they call them transcendental functions. So we're talking about exponential functions and logarithmic functions. So here's the basic exponential function. All right, so then any exponential function, provided that x is positive, not negative. If we go to infinity, what's it going to? Positive infinity. If we go to negative infinity, it's going to 0. It's going to 0. Okay? Because, right, we, like, okay. So positive infinity, I get grief. All right, so then, right, these are inverses. So this actually keeps climbing forever. So as we go to positive infinity, the y value is going to positive infinity. And then as we go to negative infinity, this one's actually going to negative infinity. And then down at the bottom of 103, they got all the statements about that. All right, 1 to 43, 9 to 43 on.